devices, most probably the syllabus of this electronic devices is we have complete electronic devices, and it's been divided into four parts: semiconductor physics, diodes, transistors, integrated circuit fabrication process. And you see here completely in electronic devices and circuits, you have total marks coming in the gate examination is 12 marks. In this, the total marks is 12 marks. The semiconductor physics is occupied by 3 marks, where you have different topics like this: energy bands, mobility, diffusion, current density, generation and recombination, Poisson and continuity equations. And the second topic is diodes. All diodes will be appearing here: PN junction, GNR, light emitting diode, photodiode, solar cell. It has been opted for 3 marks. So this is completely, you'll be getting all these marks in complete gate examination at final value. So transistors, it may be bipolar junction transistors, BJTs and MOSFETs, metal oxide semiconductor field effect transistors or FETs. Total you'll be getting 3 marks. And the last topic is integrated circuit fabrication process. This is an introduction to VLSI. This introduction to VLSI. So this introduction to VLSI, you have different process in the steps like oxidation, diffusion, ion implantation, photolithography, twin tub CMOS process. So all this you'll be having a 3 marks here. So completely you'll be getting 12 marks in electronic devices and circuits. So I hope you should divide like this into the topics, and then you should read and you should solve the problems accordingly. You should go through many textbooks, or you should go through the important materials what you have, solve the problems, and better you first you give preference to solving the problems and getting knowing that solution of that problem. Then definitely you will be going through in a front values, right? So here, this is the syllabus we have been divided, and let us start with the first topic, which is called semiconductor physics. Uh, in this, the semiconductor physics complete thing, we have actually 12 marks. No, this syllabus completely is made up of 12 marks. So therefore, so this atomic structure, we will deal with the first topic, which is called atomic structure. In this atomic structure, as you know already, I will be going step by step here. First, in atomic structure, we have an atom here. Atom, atom is a combination of nucleus plus electrons. Nucleus, this is a nucleus, and electrons are revolving around the nucleus. And this nucleus is a combination of protons plus neutrons. Nucleus is a combination of protons plus neutrons. So nucleus, proton is a positively charged particle, and a neutron is neutral. So therefore here, if you add some proton to neutron, so then it will become a positively charged particle. So therefore nucleus is always a positively charged particle here. Nucleus is always a positively charged particle, and electrons are revolving around the nucleus. And this is similar to that of a solar system. What we have, solar system, a sun and 9 planets are revolving around the sun. So therefore this nucleus is acting like a sun, and the other planets are revolving around the nucleus. So this is a first orbit. What I can say here, this is called as first orbit. First orbit, or it is also called as first shell. It is also called first shell. First orbit or first shell, where there are two electrons are revolving around the nucleus in first orbit or first shell. And similarly, this is called as second orbit. Second orbit, and it is also called as second shell. Second shell, where here 8 electrons are revolving around the nucleus. So like that, if you as you go away from the nucleus, there are various orbitals revolving, various orbitals present around the nucleus, and in that orbitals there are various electrons revolving around the nucleus. So here you can say here, one of the important competitive exam question comes over here: how many electrons are revolving around the nucleus in each orbit? So for that, we can say that the answer is 2n square. 2n square represents number of electrons. Number of electrons. 2n square represents number of electrons present in each orbit. Number of electrons in each orbit. This is what the important question, 2n square. Suppose first orbit, n is equal to 1 is said to be first orbit. If n is equal to 1 is a first orbit, how many electrons? How many electrons? 2 into 1 square, that is equal to 2 electrons. So 2 electrons are revolving around the nucleus in first orbit. N is equal to 2. How many electrons? It is equal to second orbit. So second orbit means 2 into 2 square. 2 square is 4. 4 twos are 8. 8 electrons. Likewise, n is equal to 3. N is equal to 3 means it is equal to third orbit. So third orbit means how many electrons? 2 into 3 square, 9 into 2, 18 electrons. 18 electrons are revolving around the nucleus. So one of the question asked in one of the competitive exams, like suppose n is equal to 10th orbit, how many electrons are revolving around the nucleus? How many electrons are revolving around the nucleus in 10th orbit? So in 10th orbit, n is equal to 10. So that is equal to 2 into 10 square. 100. 100 into 2, 200. 200 electrons are revolving around the nucleus. 200 electrons are revolving around the nucleus. 200 electrons are revolving around the nucleus in n is equal to 10th orbit. So likewise, the first question arises here for competitive exams, where number of electrons revolving around the nucleus. Number of electrons revolving around the nucleus. Okay, next. As you go, see here, what I am telling is this is the first orbit, first shell, second orbit, second shell. In this, again, in this first orbit there are subshells. If you know, there are subshells like S, P, D, F. These are called as subshells. These are called as subshells. These are also occupied by electrons. For example, n is equal to 2. N is equal to 2 means how many subshells? S, P, D, F. How many electrons are occupied by S actually? It is occupied by S. How many means maximum electrons? S is occupied by 2. P, how many electrons means 6. D, 10. F, 14. So please do remember this, because it might already came in the intermediate examinations or intermediate level. So please do remember this. These are very important. Now suppose S is equal to 2. These are subshells SPDF. Maximum number of electrons occupied by subshells is 2, 2 electrons, 6 electrons, 10 electrons, and 14 electrons. Now here, suppose if n is equal to 2, then you can write this one as 1s square. If n is equal to 2 is the atomic structure, n is equal to 2, then you can write it as 1s square. Likewise you need to write, because suppose n is equal to 4, then how do you write? You can write this one as 1s square plus 2s square. 1s square plus 2p2. 1s square plus 2p2, because s square plus p square, it is occupied by 2 plus electrons means 4 electrons. So likewise, there are subshells also present in each orbit. Likewise here also in second orbit there are subshells S, P, D, and F. S, P, D, F, right? So as you go away from this nucleus, see, there are certain important points that comes into existence here. Second point, what is the energy possessed by each orbit? Energy possessed by each orbit. So what is the energy possessed by each orbit? Suppose what is the energy occupied by, how do you calculate energy possessed by each orbit means you need to find how many electrons are present in that each orbit. Suppose in first orbit, how many electrons are there? In first orbit, 2 electrons are there. 2 electron means, suppose assume each electron is possessed by 1 joule. So how much of energy? 2 joules of energy is occupied by first orbit. Similarly, second orbit. Second orbit means how many electrons are there? 8 electrons are there. 8 electrons means, so how much? For example, 8 joules. So this is the energy. Now, similarly, third orbit. Third orbit means how many electrons? 18 electrons. Each electron is possessed by 1 joule. So how much of energy? 18 joules. So therefore, see here, as orbitals are increasing here, first orbit, second orbit, third orbit. What about energy? Energy possessed by each orbit is increasing. Energy possessed by each orbit is increasing. So therefore I can say that, suppose if you assume energy possessed by first orbit is E1, energy possessed by second orbit is E2, energy possessed by third orbit is E3, energy possessed by fourth orbit is E4, dash dash dash, energy possessed by nth orbit is En, then can you find the relation between energy possessed by each orbit, present in an atomic structure? It is nothing but E1 is less than E2, E2 is less than E3, E3 is less than E4, E4 is less than En dash dash dash. This, this is the second most important point for competitive exams. Second most important point for competitive exams. Right? So energy possessed by each orbits. Energy possessed by each orbits. Next, come for third case. Third case, attraction forces. Attraction forces of attraction force. What is attraction force of each orbits present in this atomic structure? So, for example, first orbit. What is the first orbit and what is attraction force? Because this is if it is nucleus, this is positively charged particle, and all electrons are negatively charged particle. They are revolving around the nucleus, right? They are attracted towards the nucleus and they are revolving around the nucleus. So therefore, what is the attraction force of first orbit? Attraction force of first orbit is very high, because it is very strong, because it is present very nearer to this nucleus. For example, sun and mercury, what is the attraction force of towards the sun? It is very fast. How many days it will take to rotate around the sun by mercury? It is approximately just 20 days. So within 20 days, mercury will get 1 year of rotation. So if it is sun, then mercury take only 20 days to revolve around the sun. So similarly, mercury, venus, earth, it will take how many days? How many days means 365 days, because it is less attracted towards the sun as that of mercury and venus if we compare. Similarly, here also the attraction forces of first orbit electrons. So if you assume attraction force of first orbit, attraction force of second orbit, attraction force of third orbit, attraction force of third orbit, attraction force dash dash dash, attraction force of nth orbit. So what will be the relation? What will be the relation means attraction force of first orbit is greater than attraction force of second orbit is greater than attraction force of nth orbit is greater than attraction force of nth orbit. So this is one of the most important relation you need to study here. Attraction forces. This is also a very important point for competitive exams, right? So as you go away from the nucleus, so one important point you need to consider here, as you are going away from the nucleus like this, you get a last orbit, which is called, this is the last orbit. You have a last orbit here like this. This is called as last orbit, or this is also called as valency orbit, because it is contained by valency electrons. It is called valency orbit or last orbit, or it is also called valency shell. It is also called valency shell, because it is contained by valency electrons, so therefore it is called valency orbit. Now can you tell me what is the attraction force of this last orbit? The attraction force of last orbit is very less. It is least attracted towards the nucleus because it is farther away from the nucleus, isn't it? It is farther away from the nucleus. It is not very nearer to the nucleus, so therefore it is farther away from the nucleus. So therefore this is called last orbit or valency orbit, and the electrons revolving around the nucleus in last orbit are called valency electrons. Valency electrons. The electrons present in last orbit are called valency electrons. The electrons present in last orbit are called valency electrons. Now let us see the case here. You can see this structure and you can take this one. We have even told that the subshells are present in this, and this is a table. You might have already seen this table here in intermediate level itself. Suppose shell K, L, M, N shells are there. K shell, N is equal to 1, number of orbit. So subshell is S, number of electrons here. What are the number of electrons here? Number of electrons are 2n square. You need to calculate by 2n square. So likewise, each shell is being filled like this, 2, 8, 18, 32, likewise it will go, right? These are all called as subshells. As I told you just now, it is contained by SPDF. So here SPDF, it is contained by SPDF. Each orbit is contained by SPDF, right? So now, so what I am doing is, I am going with the last orbit. Yes, no, I'm going with the last orbit. No. So here last orbit electrons I am dealing. Here I'm considering here last orbit. So as last orbit is farther away from the nucleus, so it is less attracted towards the nucleus. So therefore attraction force of last orbit is very less. So therefore, suppose electron is present here, electrons are present in last orbit because this is last orbit. If it is last orbit, so what happens is here, if I give certain energy to this electron, the electron which is present in last orbit, if I give certain energy to this electron, what happens is this electron goes outside and it becomes a free electron. So the electron, it takes, see, actually we need to give energy, external energy, or it takes energy from sunlight. It takes energy from sunlight in the atmosphere, and therefore this electron comes outside. If it comes outside and becomes a free electron, this electron is called as free electron, which tends for flow of electricity. This electron tends for flow of electricity, leaving here what? Leaving here hole. So it leaves a hole here and it comes outside of the atmosphere. So this is called as a free electron, which tends for flow of electricity. This tends for flow of electricity. That means which is called as current. Which is called as current. Now here this electron, this electron, it searches for a hole in the atmosphere again. Suppose it finds an atom here. If it finds an atom or atomic structure of one element, and if it finds a hole here, likewise what hole is found here, likewise if it finds an atom here, if it finds a hole here, then this electron goes and fill into this hole. This electron goes and fill into this hole. Now this hole is filled with electron, leaving here what hole. Again it takes energy. Again it jumps and again it becomes a free electron. Again it searches for a hole in the atmosphere. Again it searches for a hole in the atmosphere. If it finds a hole, again it leaves a hole here. Again it goes and jumps and fill this hole here. So likewise you can observe here, electron, if it is becoming a free electron, again again it is going and filling this hole here. So again leaving here, it is filling a hole. Again it takes energy. Again it goes and fill a hole here, leaving here hole. So again likewise it's a continuous process. Again it leaves a hole here. Again it fills a hole here. So likewise you can observe here, electron journey is from left towards right. It's just for an example, left towards right, left to right, right? So electron is moving in this direction. So if it is happened continuously, what happens? If it is happened continuously, then electron current is generated. If it is happened continuously, electron current is generated, because continuously if it is happening, it's just only microsecond is there in between the gap of this hole and this hole. So therefore electron current is generated. That current is called electron current. Now similarly, you go from right to left. You go from right to left. What are moving from right to left? A hole is moving. See, this is a hole. 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 So therefore, even if you combine all these holes, there is another current which is called as hole current. Hole current is created. So now we can obtain total current here. What is the total current obtained here? Total current is equal to electron current plus hole current. Electron current plus hole current. So this is most important. Likewise, electron current is generated in atomic structures, and that current we are observing in our houses, in the wires, in switchboards and all this. So this is called as total current, electron current plus hole current, right? So if electrons are maximum, then current is due to electrons. If holes are maximum, current is due to holes. That we will study anyhow in the future classes. So this is how the current is generated in atomic structure, right? This is how the current is generated in atomic structure. Now here, the most important point is the total current is nothing but here the electron current plus hole current, and 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 remember, only this electron current and hole current is due to generation of free electrons. This is very important. Only due to free electrons only the current is generated. This is very important point for competitive exams. Only due to free electrons current is generated, right? Now now let us study about this is what the total current. Let us go with the energy bands actually. Let us study about energy band. What is a band? Band means group. Just now I spoke with the energies. Energy means the energy possessed by an electron. Band means group of energy. Suppose, what is the energy band of first orbit? What is the energy band of first orbit? Or what is the first energy band? First energy band. First energy band means first orbit energy. How do you calculate first orbit energy? By merging energies of all electrons present in first orbit. If you merge all the energies of electrons present in first orbit, how many electrons are present in first orbit? How many electrons are present in first orbit? Only two electrons. So merge all the energies of first orbit, 1 plus 1, for example, you get 2 joules. So this is called as first energy band. First energy band. Likewise, second energy band. What is second energy band? Merging of energies of all electrons present in second orbit. So how many electrons are there in second orbit? 8 electrons. Merge all those energies of 8 electrons. 1 plus 1 plus 1 plus 1. Likewise, plus 1. How many joules you get? 8 joules you get. This is called as second energy band. This is called a second energy band. Likewise, if you go, you will get a valency energy band. So what is the last orbit? You get a valency energy band or valency band. So what is the valency band? Merging of energies of valency electrons. Merging of energies of valency electrons, you get what band? Valency band. Right. After valency band, what is the band present? Suppose this is a valency orbit. Just now we have talked with the last orbit here. After valency band, the electron is becoming free. So here, this free electron is present in which state? It is in conduction state. It is in conduction state because that electron only conducts for flow of electricity. So it is in conduction state. So you can merge all the electrons present in conduction state. Merge all the electrons present in conduction state, then it will form a band. So what is that band? That band is called what? That band is called what? Merging of energies present in conduction band. Conduction state, sorry, conduction state. So it will form a conduction band, that is called as conduction band, right? So after first energy band, you will get a second energy band. After second energy, third energy band. After third energy, valence energy band. After valence energy band, conduction energy band or conduction band. So this is what the energy band structure. Then now we'll be looking about this energy bands like this here. So here what I am doing is I am taking on x-axis the edge of the nucleus, and on y-axis I am taking energy. You see here, this is the energy and this is the edge of the nucleus, which is nothing but nucleus, edge of the nucleus. Now if I take this one as x-axis and this one as y-axis, this is a starting point of 0, edge of the nucleus. This is a starting point, energy 0 joules, because energy always it is represented in joules, right? Energy is always represented in joules. Now what happens? Edge of the nucleus, you have 0 joules. What is the edge of the nucleus? You see this structure here. You see the structure. What is the energy present at this point? Is there any electron revolving at this point? No. So no electron means what is the energy? 0 joules. Now here, first orbit. First orbit means how many joules of energy? 2 joules of energy. How many joules of energy? 2 joules of energy. This is second orbit. How many joules of energy? 8 joules of energy. Now I am representing in terms of energies here. This is first band. How many joules? 2 joules. So this is again second band. How many joules? 8 joules. This is third band. How many joules? 18 joules. Likewise, the x y-axis goes here because, isn't it? So here, because the first band energy, it's only 2 joules. That's what after 0 you have first band energy, which is 2 joules. So this is the line. Next, after 2 joules, what is the second band energy? It is of 8 joules. So therefore that's what it is lying here. It is lying here. This is a first band, this is second band, and this is third band. What is the third band? It is of 18 joules. So 18 joules means it is coming over here. Likewise, if you go, Likewise, if you go top, you have what band? Valence band. Because valence electrons, all energies you are merging, so you will get a valence band, energy band, right? Next, next you will be going, say, after valence band, electron is jumping from valence band to conduction band. You are merging all the energies of conduction band here, so you get conduction band here. So this is valence band and this is conduction band, merging of all the energies present in the free electrons, so it's a conduction band. So here is important points you need to remember here is valence band energy level is given by EV. E means energy, suffix V means valence band. Here conduction band energy is given by EC. E means energy, again C means conduction band here. So what is the gap between valence band and conduction band? It is called EG. It is called energy gap EG. Energy gap EG, it's also called forbidden energy gap. This gap is called forbidden energy gap. That gap is called forbidden energy gap. That gap is called forbidden energy gap and it is given by EG. EG, right? Now the important points come here into existence here. So I hope you have understood this energy band structure here. Edge of the nucleus I am taking at starting point. Next, first level, second level, third level, fourth level, fifth level. Likewise, it goes, and valency band it comes, and then conduction band it came. Right. So what is the highest energy band now here? Highest energy band is conduction band. Least energy band is first orbit energy band. First orbit energy band. Now, got it all of you? Is it clear all of you? I don't have any response from you. Is it clear all of you? Are you getting ma?
Yes, sir. Clear, sir.
Yeah. If you have any doubt, please let me know that. Okay. Don't sit silently. Okay. Now, see, we are going deep into the subject. Now, actually, every point what I am speaking is very important for you, ma. Because at most, probably maximum questions will be asked in semiconductor physics in various competitive exams. So this energy band structure is also very important for you, right? So now here, there comes here, according to this energy band, there comes here three cases. Three cases. These cases are very important. First case, energy gap, forbidden energy gap, EG. Energy gap is approximately equal to 6 electron volts. 6 electron volts. Now, if energy gap is approximately equal to 6 electron volts, what happens? If energy gap is approximately equal to 6 electron volts, then that type of system is called as an insulator. Very, very important. If energy gap is approximately equal to 6 electron volts, the type of system is called an insulator. An insulator. Because see, what is an insulator? For example, see here, this is what valency band, and this is what conduction band, and the gap between valency band and conduction band is Eg. This gap, energy gap, is 6 electron volts. If it is equal to 6 electron volts, then it is called as an insulator. What are best examples of insulator, ma? Best examples of insulators are, what are best examples? Carbon. Carbon is the best example. Diamond. Diamond is the best example of insulators. These are technical examples. Natural examples are wood, plastic. These are natural examples. So here, carbon, diamond, wood, plastic, if you consider, it does not carry any electricity because its energy gap is approximately equal to 6 electron volts. That means there is a large gap between valence band and conduction band. So if electrons are present in valence band, if I give certain energy externally, this electron cannot jump from valence band to conduction band. And this electron cannot become a free electron. So when electricity is flown, only the electron, if it becomes a free. But here, if I give external energy or apply certain temperature, this electron cannot jump from valence band to conduction band, provided that it will not reach 6 electron volts. It will not reach 6 electron volts. So therefore, that's what. So any type of device which have possess energy gap of 6 electron volts, those are called as insulators. Those are called as insulators. Best examples are carbon, diamond, wood, plastic, and everything else. These are called as technical examples. These are called natural examples. Right? Now, similarly here, there appears case 2. Exam energy gap is approximately equal to 1 electron volt. 1 electron volt. That means here, forbidden energy gap is decreasing. Here, this forbidden energy gap is called Eg. That Eg is been decreased. Previously, you have a conduction band here, and here you have valence band here. Right? See the gap here. Compare with first one and second case. What is the gap here? This is Eg. This Eg is approximately equal to how much? 1 electron volt. Now this is very less. Suppose an electron is present in valence band. If I apply certain energy here to this electron, this electron definitely jumps from valence band to conduction band, and it is going to fill a hole in valence band here, conduction band here. Right. So likewise, electron can jump from valence band to conduction band, provided that its energy gap is equal to 1 electron volt. So this type of devices are called semiconductors. This type of devices are called semiconductors. This type of devices are called semiconductors. Because until unless if you apply external energy, no current is flown in the device. So that's what it is called semi. It's a semiconductor. Semi means half. So it is acting like an insulator, and also it is acting like a conductor. If you give certain, if you does not give any energy, it is acting like an insulator. If you give energy, then electron jumps from valence band to conduction band, then it is acting like a conductor. So that's what it is called as a semiconductor. Semiconductor. Examples. What are examples of semiconductors? Examples of semiconductors. Technical examples are silicon, germanium, germanium. These are single crystal semiconductors. Remember, these are single crystal semiconductors. Individual semiconductors means single crystal semiconductors. And there are also compound semiconductors like gallium arsenide, gallium nitride, gallium arsenide phosphide, right? Gallium phosphide. These are compound crystal semiconductors. These are called compound crystal semiconductors. These are called compound crystal semiconductors, right? So we are learning about two types of semiconductors here: silicon, germanium, single crystal semiconductors. Compound crystal semiconductors are gallium arsenide, gallium nitride, gallium arsenide phosphide, gallium phosphide. There come certain questions in competitive exams like this. Name some semiconductors in the following list. They will be asking: A. Silicon, B. Germanium, C. Gallium arsenide, D. All the above. So your option should be all the above, because even gallium arsenide is also a semiconductor. No, it is also acting like a compound crystal semiconductor, right? So you should be knowing about compound crystal semiconductors also. It is one of the question asked in one of the competitive exams. Please do remember, right? So there are also compound crystal semiconductors. So this is called as a semiconductor. Now, in this semiconductor, I can say that this semiconductor is having and it is possessing a negative temperature coefficient. All semiconductors possess negative temperature coefficient. This is very important point for gate point of view. Negative temperature coefficient. All semiconductors possess negative temperature coefficient. What is this negative temperature coefficient? Let us see. What is this negative temperature coefficient? Okay. All semiconductor materials have negative temperature coefficient. So what is this negative temperature coefficient? Okay. See, negative temperature coefficient means it's a relation between temperature and resistance. It's a relation between temperature and resistance. Okay, what is negative temperature means? As temperature is increased, what happens to resistance? Decreases. As temperature is increased, resistance decreases. This is called negative temperature coefficient. So what should be the graph here? As temperature is increased, suppose 0, it is increasing like this. What should be the resistance? It should decrease like this. It should decrease. It should decrease like this. So this is the graph for negative temperature coefficient. So how do you get a negative temperature coefficient like this means? Now here what I told means the semiconductors, this is acting like a conduction band and this is acting like a valence band. Now I told you already this is energy EV and this is energy EC. Always do remember here another important question here. Always EC is greater than EV. Always energy of conduction band is greater than energy of valency band. Please do remember this one. Energy of conduction band is greater than energy of valency band. Right? Next, see what happens is uh, here electrons are present. So I am giving certain external energy. So this electron jumps and goes to conduction band and fill over here. In turn creates a current. Kada. So current is created here. Electricity is created here. Current is created means what happens? Conductivity takes place. Conductivity takes place. Since there is a gap here, so there is a possibility that more number of electrons will jump from valence band to conduction band. In turn, conductivity increases. More charge carriers are created in conduction band. More charge carriers. I repeat this point. More charge carriers are created. More charge carriers are created in conduction band. If more charge carriers are created in conduction band, conductivity rises. Conductivity rises. So conductivity rises means what about conductivity? It's a current, no. Conductivity is increasing. Conductivity is increasing means what about resistance? Decreases. Resistance decreases because I is equal to V is equal to IR we have. V is equal to IR. I is equal to what? V by R. Conductivity is increasing means resistance should be decreased. When conductivity increases, because temperature is increasing, no. Temperature means external energy. We are applying external energy in the form of temperature. So if you apply external energy in the form of temperature, all electrons present in valence band jumps and fill into this conduction band. So therefore, temperature increases, current increase, conductivity increases. Conductivity increases, what happens? Resistance decreases. Temperature increases, conductivity. Remember this point, conductivity increases. Conductivity increases and the resistance decreases. This is happened only in semiconductors. This is happened only in semiconductors, and therefore all semiconductors, I can say all semiconductors possess negative temperature coefficient. All semiconductors possess negative temperature coefficient. Right? Next. All semiconductors, another important point for competitive exams. All semiconductors at 0 degree Kelvin. Semiconductors at T is equal to 0 degree Kelvin act like dash. Act like dash. Anyone?
Insulator.
Very good. They are acting like insulators because we are not giving any temperature. No. Here we are increasing the temperature, so therefore conductivity is increasing and therefore resistance is decreasing. So therefore it is acting like negative temperature coefficient. But here we are not increasing any temperature. So therefore electrons are present there itself in valence band. So therefore at T is equal to 0 degree Kelvin, all semiconductors acts like insulators. Very, very, very important point for competitive exams. All semiconductors at T equal to temperature 0 degree Kelvin act like insulators. Insulators. Again, second point. This is first point. Second point. Semiconductors, as temperature increases, all semiconductors becomes what? All semiconductors, as temperature increases, becomes what? Becomes
Conductors.
Conductors. Good. Becomes conductors. This is also very important point. 2 points are important. 2 points are important, right? Becomes conductors. Now here, what happens is here, I am increasing the temperature here. If I increase the temperature, electron is jumping from valence band to conduction band. That means what happens to energy gap Eg? What happens to energy gap Eg? Here, as temperature is increased, here, as temperature is increased here, as temperature is increased, What happens to energy gap? It is increasing or decreasing? It is decreasing. Energy gap is
Decrease.
decreasing, right? By how much quantity it decreases actually? That is important here. Okay, so there comes a gate question here. As temperature, third point, as temperature increases, energy gap decreases in semiconductors, isn't it? Because we are learning about semiconductors, no? So as temperature is increased, energy gap decreases, and it decreases differently for both germanium and silicon. For example, silicon, if you take, if material is made up of with silicon, then energy gap for every 1 degree C rise in temperature, it decreases by 3.6 into 10 power minus 4. 3.6 into 10 power minus 4 for every degree C rise in temperature. Please, important point, very important point, very important point. Please note it. For silicon, energy gap, silicon energy gap for every 1 degree C rise in temperature, it decreases by 3.6 into 10 power minus 4. 3.6 into 10 power minus 4 electron volts per degree C. Sorry, it is electron volts per degree C. So energy gap is being decreased by 3.6 into 10 power minus 4 electron volts per degree C. Similarly for germanium, for germanium, energy gap decreases because we are increasing temperature, no? Even for germanium also. So as temperature increases, germanium energy gap decreases. So how much quantity means for every 1 degree C rise in temperature, it decreases by 2.23 into 10 power minus 4 electron volts per degree C. So it decreases by 2.23 into 10 power minus 4. 2.23 into 10 power minus 4. Likewise, there comes here important points, important problems. There comes here, for example, fourth point, fourth important point is what is what is energy gap? What is energy gap for silicon? Let us learn for silicon. What is energy gap for silicon at room temperature? At room temperature means at T is equal to 27 degrees C. At T is equal to 27 degrees C. So there is a formula here. The formula is important. Eg is equal to Eg naught minus beta into capital T. So what is Eg naught? Eg naught means energy gap at 0 degree Kelvin. So what is energy gap at 0 degree Kelvin of silicon means it is approximately equal to 1.21 electron volts. Eg naught is 1.21. Energy gap at 0 degree Kelvin, it is equal to 1.21. This is a default value, 1.21 electron volts. So energy gap at 0 degree Kelvin is 1.21 minus beta. Beta means this one. How much quantity the energy gap is decayed. It is equal to 3.6 into 10 power minus 4 into capital T. Capital T should always be in degree Kelvin. So that is equal to, we have taken 27 degrees C plus 273. Convert into kelvins, that is equal to 300 degree Kelvin. 300 degree Kelvin. So multiply here into 300 into 300. So tell me what is the answer. It is equal to what you get. So energy gap of silicon at room temperature is how much? It is equal to, if you do it, it is equal to 1.1 electron volts. Very important point. Energy gap of silicon at room temperature. At room temperature, this is at room temperature means T is equal to 300 degree Kelvin. This is called room temperature in degree Kelvin. So energy gap of silicon at room temperature is 1.1 electron volts, and energy gap at 0 degree Kelvin at temperature T is equal to 0 degree Kelvin is 1.21 electron volts. Please do remember these important points. Similarly for germanium. Similarly for germanium, that is for silicon. Similarly for germanium, what do you do for germanium? Similarly for germanium, how do you write for germanium? For germanium, how do you write for germanium? Eg is equal to Eg is equal to, this is which point? Fifth point. This is fifth important point. Eg is equal to Eg is equal to Eg naught. Eg is equal to Eg naught minus beta into T. That is equal to, what is Eg naught? 0.785 electron volts. Please do remember, Eg naught of germanium is 0.785 electron volts. Beta, what is beta? How much energy gap it has been decayed? It has been decayed by 2.23 into 10 power minus 4. 2.23 into 10 power minus 4. 2.23 into 10 power minus 4 into capital T. How much? 300 degree Kelvin. So find it answer. What is the answer? Eg is equal to, what do you get?
0.71.
Yes, 0.72.
71 meter. Okay.
0.72 electron volts. Okay, it's not 0.71. 719 you get, I think 718, 719. So it has been written as
71
0.72 electron volts. So please do remember this important point. Energy gap of germanium at 300 degree Kelvin at room temperature, that is T is equal to 300 degree Kelvin, you get an answer 0.72 electron volts. At 0 degree Kelvin you put T is equal to 0, then what you get? Eg is equal to Eg naught, that is equal to 0.785 electron volts. That is equal to 0.785 electron volts. So these are very important points that you need to remember for competitive exams. And semiconductor materials all are having a negative temperature coefficient. These are all important points what we are learning here. Okay. Next, similarly, these are about details about semiconductors. Next, come to conductors. Conductors, I told you already. Conductors, we are learning about energy band gaps kada, energy band theory we are learning. So let us learn about conductor. Here the gap, energy gap we are learning. Energy gap we are learning. If energy gap is approximately equal to 6 electron volts, it is called it is called insulator. It is called insulator. If energy gap is approximately equal to 1 electron volt, it is called semiconductor. Energy gap is equal to 0 electron volts, then it is called what? Conductor. Then it is called conductor. So that means there is no energy gap. There is no energy gap means what happens? If you observe here from this point to this point, if this is a conduction band, here EC lies, where does valency band lies? Valency band lies from this point to this point, this point to this point. So here EV lies. So what about EC and EV? They are overlapping with each other. They are overlapping with each other. Actually, where electrons are present in valence band, electrons are present in valence band. They need to jump from valence band to conduction band. But here there is no need of jumping from valence band to conduction band, right? Because already electrons are also present in conduction band, because they are overlapping. Because they are overlapping. Why they are overlapping means because energy gap is equal to 0 electron volts. So if energy gap is equal to 0 electron volts, they are called as conductors. They are called as conductors. Examples. Examples of conductors, all metals. All metals are examples of conductors. Natural example is iron. aluminum, iron. All metals are examples of conductors. Iron is the best example, natural example. So here one important point is all conductors possess positive temperature coefficient. All conductors possess a positive temperature coefficient. What is positive temperature coefficient? It tells you the relation between temperature and resistance. So as temperature is increased, positive means what? It is increasing. So temperature is increased, resistance also increases. As temperature is increased, resistance increases. But what about here? Resistance increase means what about conductivity? What about conductivity? Conductivity decreases. Conductivity decreases. Means here, one important point here, because conduction band and valence band are overlapped here, are overlapped. Conduction band and valence band are overlapped. This is EC and this one is EV, overlapped. Here, the relation temperature is increased, resistance is increased means you can draw a curve like this. This is temperature and this is resistance. And as temperature is increased, it is going from 0 to certain value, resistance increases like this. This is the graph for conductors which are having positive temperature coefficient. And here why this resistance is increasing means the vibration pattern. See, suppose there are electrons present here, there are electrons present here. If there are electrons present here in this uh, valence band, suppose if I give certain energy, what happens is there is no free space to move for these electrons from conduction valence band to conduction band. There is no free space. So what happens? They will collide with one another. Just they will collide with one another, and therefore they will stay there itself. But it's not happened like this in semiconductors. There is a large gap between conduction band and valence band here. What is that gap? It is approximately equal to 1 electron volt. So if I give certain energy in semiconductor, this electron jumps into conduction band because there is a gap here. But here, since there is no gap, because all are filled with electrons here, all are filled with electrons. So therefore, if I give certain energy, external energy, temperature, this electron collides with another electron. It does not move from this point to this point, isn't it? So that moment decreases. Moment of charge carriers decreases. That moment decreases means conductivity decreases. That conductivity decreases means resistance increases. So therefore, as temperature is increased, moment of the charge carriers decreases and conductivity decreases. So therefore, resistance increases. So therefore, I can say that all conductors possess positive temperature coefficient, right? So there is, because there is no space here. One of the important point is there is no space here, whereas here in a semiconductor it is present space. So that's what they can jump from one point to another. But here there is no space. They will collide with one another. So moment of the charged particles is very less. So that moment of charged particles is very less means so therefore vibration, due to that vibration pattern, conductivity decreases, resistance increases, and therefore this is the relation of conductors. Temperature increases, resistance increases. So all conductors possess positive temperature coefficients. Positive temperature coefficients. So this is about today's class. We'll stop over here for today.